Rounding a numerical value means replacing it by another value that is approximately equal but has a shorter, simpler, or more explicit representation. For example, replacing £23 4,476 with £23.45, or the fraction 312 937 with 1/3, or the expression square root 2 with 1.414. Rounding is often done to obtain a value that is easier to report and communicate than the original. Rounding can also be important to avoid misleadingly precise reporting of a computed number, measurement or estimate. For example, a quantity that was computed as 123,456 but is known to be accurate only to within a few hundred units is better stated as about 123,500. On the other hand, rounding of exact numbers will introduce some round-off error in the reported result. Rounding is almost unavoidable when reporting many computations, especially when dividing two numbers in integer or fixed-point arithmetic, when computing mathematical functions such as square roots, logarithms, and sines, or when using a floating-point representation with a fixed number of significant digits. Accurate rounding of transcendental mathematical functions is difficult because the number of extra digits that need to be calculated to resolve whether to round up or down cannot be known in advance. This problem is known as the table maker's dilemma. Rounding has many similarities to the quantization that occurs when physical quantities must be encoded by numbers or digital signals. A wave equals sign is sometimes used to indicate rounding of exact numbers. For example, 9.9810. Types of rounding. Typical rounding problems are approximating an irrational number by a fraction, e.g., pi by 22/7, approximating a fraction with periodic decimal expansion by a finite decimal fraction, e.g., 5/3 by 1.6667, replacing a rational number by a fraction with smaller numerator and denominator, e.g., 3122 9417 by 1/3, replacing a fractional decimal number by one with fewer digits, e.g., by $2.18, replacing a decimal integer by an integer with more trailing zeros, e.g., 23,217 people by 23,200 people, or, in general, replacing a value by a multiple of a specified amount, e.g., 48.2 seconds by 45 seconds. Rounding to a specified increment. The most common type of rounding is to round to an integer, or, more generally, to an integer multiple of some increment, such as rounding to whole tenths of seconds, hundredths of a dollar, to whole multiples of 1/2 or 1/8 inch, to whole dozens or thousands, etc. In general, rounding a number x to a multiple of some specified increment m entails the following steps. Divide x by m, let the result be y. Round y to an integer value, call it q. Multiply q by m to obtain the rounded value z. For example, rounding x equals to whole cents entails computing y equals by per meter equals 2.1784, 0.01 equals 217.84, then rounding y to the integer q equals 218. And finally computing z equals q times m equals 218 times 0.01 equals 2.18. When rounding to a predetermined number of significant digits, the increment m depends on the magnitude of the number to be rounded. The increment m is normally a finite fraction in whatever number system is used to represent the numbers. For display to humans, that usually means the decimal number system. For intermediate values stored in digital computers, it often means the binary number system. The abstract single argument round function is formally defined here, but in many cases it is used with the implicit value m equals 1 for the increment and then reduces to the equivalent abstract single argument function, with also the same dozen distinct concrete definitions. Rounding to integer. The most basic form of rounding is to replace an arbitrary number by an integer. All the following rounding modes are concrete implementations of the abstract single argument round. Q is the largest integer that does not exceed y. Round up. Q is the smallest integer that is not less than y. Round towards 0. Q is the integer part of y, without its fraction digits. Round away from 0. If y is an integer, q is y, else q is the integer that is closest to 0 and is such that y is between 0 and q. Round to nearest. Q is the integer that is closest to y. The first four methods are called directed rounding, as the displacements from the original number y to the rounded value q are all directed towards or away from the same limiting value. If y is positive, round down is the same as round towards 0, and round up is the same as round away from 0. If y is negative, round down is the same as round away from 0, and round up is the same as round towards 0. In any case, if y is integer, q is just y. Where many calculations are done in sequence, the choice of rounding method can have a very significant effect on the result. A famous instance involved a new index set up by the Vancouver Stock Exchange in 1982. It was initially set at 1000.000, and after 22 months had fallen to about 520, whereas stock prices had generally increased in the period. The problem was caused by the index being recalculated thousands of times daily, and always being rounded down to 3 decimal places, in such a way that the rounding errors accumulated. Recalculating with better rounding gave an index value of 1098.892 at the end of the same period. Tiebreaking rounding a number y to the nearest integer requires some tiebreaking rule for those cases when y is exactly halfway between two integers, that is, when the fraction part of y is exactly 0.5. Round half up. The following tiebreaking rule, called round half up, is widely used in many disciplines. That is, halfway values y are always rounded up. If the fraction of y is exactly 0.5, then q equals y plus 0.5. For example, by this rule the value 23.5 gets rounded to 24, but minus 23.5 gets rounded to minus 23. However, some programming languages define half_up as round half away from 0. If it were not for the 0.5 fractions, the round-off errors introduced by the round to nearest method would be symmetric. For every fraction that gets rounded up, there is a complementary fraction that gets rounded down by the same amount. When rounding a large set of numbers with random fractional parts, these rounding errors would statistically compensate each other, and the expected value of the rounded numbers would be equal to the expected value of the original numbers. However, the round half-up tiebreaking rule is not symmetric, as the fractions that are exactly 0.5 always get rounded up. This asymmetry introduces a positive bias in the round-off errors. For example, if the fraction of y consists of 3 random decimal digits, then the expected value of q will be 0.0005 higher than the expected value of y. For this reason, round to nearest with the round half-up rule is also known as asymmetric rounding. One reason for rounding up at 0.5 is that for positive decimals, only the first figure after the decimal point needs be examined. For example, when looking at 17.5000, the 5 alone determines that the number should be rounded up to 18 in this case. This is not true for negative decimals, such as -17.5000, where all the fractional figures of the value need to be examined to determine if it should round to -17 or to -18. Round half down. One may also use round half down as opposed to the more common round half up. If the fraction of y is exactly 0.5, then q equals y minus 0.5. For example, 23.5 gets rounded to 23, and minus 23.5 gets rounded to minus 24. The round half-down tie-breaking rule is not symmetric, as the fractions that are exactly 0.5 always get rounded down. This asymmetry introduces a negative bias in the round-off errors. For example, if the fraction of y consists of 3 random decimal digits, then the expected value of q will be 0.0005 lower than the expected value of y. For this reason, round to nearest with the round half-down rule is also known as asymmetric rounding. Round half towards 0, 1 may also round half towards 0 as opposed to the conventional round half away from 0. If the fraction of y is exactly 0.5, then q equals y minus 0.5 if y is positive, and q equals y plus 0.5 if y is negative. For example, 23.5 gets rounded to 23, and minus 23.5 gets rounded to minus 23. This method also treats positive and negative values symmetrically, and therefore is free of overall bias if the original numbers are positive or negative with equal probability. Round half away from 0. The other tie-breaking method commonly taught and used is the round half away from 0, namely, if the fraction of y is exactly 0.5, then q equals y plus 0.5 if y is positive, and q equals y minus 0.5 if y is negative. For example, 23.5 gets rounded to 24, and minus 23.5 gets rounded to minus 24. This method treats positive and negative values symmetrically, and therefore is free of overall bias if the original numbers are positive or negative with equal probability. It is often used for currency conversions and price roundings, as it is easy to explain by just considering the first fractional digit, independently of supplementary precision digits or sign of the amount. Round half to even. A tie-breaking rule that is less biased is round half to even, namely, if the fraction of y is 0.5, then q is the even integer nearest to y. Thus, for example, plus 23.5 becomes plus 24, as does plus 24.5, while minus 23.5 becomes minus 24, as does minus 24.5. This method treats positive and negative values symmetrically, and is therefore free of sign bias. More importantly, for reasonable distributions of y values, the expected value of the rounded numbers is the same as that of the original numbers. However, this rule will introduce a towards 0 bias when y minus 0.5 is even, and a towards infinity bias for when it is odd. This variant of the round to nearest method is also called unbiased rounding, convergent rounding, statistician's rounding, Dutch rounding, Gaussian rounding, odd-even rounding, or banker's rounding. This is the default rounding mode used in IEEE 754 computing functions and operators. Round half to odd. A similar tie-breaking rule is round half to odd. If the fraction of y is 0.5, then q is the odd integer nearest to y. Thus, for example, plus 23.5 becomes plus 23, as does plus 22.5, while minus 23.5 becomes minus 23, as does minus 22.5. This method also treats positive and negative values symmetrically, and is therefore free of sign bias. More importantly, for reasonable distributions of y values, the expected value of the rounded numbers is the same as that of the original numbers. However, this rule will introduce a towards 0 bias when y minus 0.5 is odd, and a towards infinity bias for when it is even. This variant is almost never used in computations, except in situations where one wants to avoid rounding 0.5 or minus 0.5 to 0, or to avoid increasing the scale of floating point numbers. which have a limited exponent range. With round half to even, a non-infinite number would round to infinity, and a small d normal value would round to a normal non-zero value. Effectively, this mode prefers preserving the existing scale of tine numbers, avoiding out-of-range results when possible for even-based number systems. Stochastic rounding. Another unbiased tie-breaking method is stochastic rounding. If the fractional part of y is 0.5, choose q randomly among y plus 0.5 and y minus 0.5 with equal probability. Like round half to even, this rule is essentially free of overall bias, but it is also fair among even and odd q values. On the other hand, it introduces a random component into the result. Performing the same computation twice on the same data may yield two different results. Also, it is open to non-conscious bias if humans are randomly deciding in which direction to round. Alternating tie-breaking. One method, more obscure than most, is round half alternatingly. If the fractional part is 0.5, alternate round up and round down. For the first occurrence of a 0.5 fractional part, round up. For the second occurrence, round down, so on so forth. This suppresses the random component of the result. If occurrences of 0.5 fractional parts can be effectively numbered, but it can still introduce a positive or negative bias according to the direction of rounding assigned to the first occurrence, if the total number of occurrences is odd. Dithering and error diffusion. When digitizing continuous signals, for example images or sound, the overall effect of a number of measurements is more important than the accuracy of each individual measurement. In these circumstances, dithering, and a related technique, error diffusion, are normally used. A related technique called pulse width modulation is used to achieve analog-type output from an inertial device by rapidly pulsing the power with a variable duty cycle. Error diffusion tries to ensure the error on average is minimized. When dealing with a gentle slope from 1 to 0, the output would be 0 for the first few terms until the sum of the error and the current value becomes greater than 0.5, in which case a 1 is output and the difference subtracted from the error so far. Floyd-Steinberg dithering is a popular error diffusion procedure when digitizing images, rounding to simple fractions. In some contexts it is desirable to round a given number x to a neat fraction, that is, the nearest fraction z equals m, n whose numerator m and denominator n do not exceed a given maximum. This problem is fairly distinct from that of rounding a value to a fixed number of decimal or binary digits, or to a multiple of a given unit m. This problem is related to fairy sequences, the Sternbrock-Oat tree, and continued fractions. Scaled rounding. This type of rounding, which is also named rounding to a logarithmic scale, is a variant of rounding to a specified increment. Rounding on a logarithmic scale is accomplished by taking the log of the amount and doing normal rounding to the nearest value on the log scale. For example, resistors are supplied with preferred numbers on a logarithmic scale. For example, for resistors with 10% accuracy they are supplied with nominal values 100, 121, 147, 178, 215 etc. If a calculation indicates a resistor of 165 ohms is required, then log equals 2.167, log equals 2.217 and log equals 2.250. The logarithm of 165 is closer to the logarithm of 178, therefore a 178 ohm resistor would be the first choice if there are no other considerations. Round to available value. Finished lumber, writing paper, capacitors, and many other products are usually sold in only a few standard sizes. Many design procedures describe how to calculate an approximate value, and then round to some standard size using phrases such as round down to nearest standard value, round up to nearest standard value, or round to nearest standard value. when a set of preferred values is equally spaced on a logarithmic scale. Choosing the closest preferred value to any given value can be seen as a kind of scaled rounding. Such rounded values can be directly calculated. Floating point rounding. In floating point arithmetic, rounding aims to turn a given value x into a value z with a specified number of significant digits. In other words, z should be a multiple of a number m that depends on the magnitude of x. The number m is a power of the base of the floating point representation. Apart from this detail, all the variants of rounding discussed above apply to the rounding of floating point numbers as well. The algorithm for such rounding is presented in the scaled rounding section above, but with a constant scaling factor s equals 1, and an integer base b greater than 1. For results where the rounded result would overflow the result for a directed rounding is either the appropriate signed infinity, or the highest representable positive finite number, depending on the direction of rounding. The result of an overflow for the usual case of round to nearest is always the appropriate infinity. Double rounding. Rounding a number twice in succession to different precisions, with the latter precision being coarser, is not guaranteed to give the same result as rounding once to the final precision except in the case of directed rounding. For instance, rounding 9.46 to 1 decimal gives 9.5, and then 10 when rounding to integer using rounding half to even, but would give 9 when rounded to integer directly. Borman and Chatfield discuss the implications of double rounding when comparing data rounded to 1 decimal place to specification limits expressed using integers. In Martinez v. Allstate and Sendeo v. Farmers, litigated between 1995 and 1997, the insurance companies argued that double rounding premiums was permissible and in fact required. The U.S. courts ruled against the insurance companies and ordered them to adopt rules to ensure single rounding. Some computer languages and the IEEE 754-2008 standard dictate that in straightforward calculations the result should not be rounded twice. This has been a particular problem with Java as it is designed to be run identically on different machines. Special programming tricks have had to be used to achieve this with x87 floating point. The Java language was changed to allow different results where the difference does not matter and require a strict FP qualifier to be used when the results have to conform accurately. Exact computation with rounded arithmetic. It is possible to use rounded arithmetic to evaluate the exact value of a function with a discrete domain and range. For example, if we know that an integer n is a perfect square, we can compute its square root by converting n to a floating point value x, computing the approximate square root y of x with floating point, and then rounding y to the nearest integer q. If n is not too big, the floating point round-off error in y will be less than 0.5, so the rounded value q will be the exact square root of n. In most modern computers, this method may be much faster than computing the square root of n by an all-integer algorithm.